at 0. That condition is 0. Helge made this condition not because he wanted to restrict the class of, because formulas become more complicated and more tricky with when you have this A. First, A is not 0, not necessarily 0, might be 0, but and then f of A is not necessarily 0. I mean, it's better not actually. But formulas become more complicated, and this the Linde's question, that relation between simple model and this blue is slightly more complicated than what was in that one of the slides of Helge. So but it will appear here. So class of kernels, it's not general kernel. This is a so-called triangular or whatever, factorable or whatever kernels, plus this is Markovian processes basically, plus conditionally Markovian processes, which I try to mention at the end. But if I forget, Valery will ask me anyway. Like Brownian bridge.
My questions are removed because you have considered a very special type of kernel, so which is.
Yeah, these ones, yes. So basically any U, any V, but which is any Markovian whatever process, but also so-called conditionally Markovian can be included into this consideration. Conditionally Markovian, if you fix some point somewhere, it becomes Markovian, which is Brownian bridge.
Because Sachs and Ilvisaker, they consider kernels of.
They consider different. Yeah, they consider okay. Sachs and Ilvisaker considered their approach was different. So they basically were interested only in the design. In the end, for blue, we don't have blue. We don't do discrete blue. So they had discrete blue, and they had all these Hilbert spaces with radioactive kernels. They assumed some derivatives at 0, the covariance function, and they considered choice of points for blue. However, I will try to claim somewhere that we are better than Sachs-Ilvisaker.
Maybe for that type of kernel.
Yes, or maybe for Brownian bridge, which is more doubtful, but we can. I can show what happens there. I mean, maybe on the blackboard. It's not in the slides. Anyway, regression model. What is my pointer? Because this one doesn't work. That one is what Helge considered the continuous version, and this is a discrete version. Okay. And this is my kernel. Standard estimators. Okay, tutorial for first year undergraduate or whatever. So that is weighted least square, general weighted. W is any matrix you want, so that one is non-degenerate. This is the covariance matrix of weighted least square. So why weighted least square is good? Because it minimizes weighted sum of square. That's what textbooks say. So particular cases of this weighted least square is ordinary, O for ordinary here. That one doesn't take into account covariance matrix of covariances. That is blue, discrete blue. Blue here is discrete blue. And that is an estimator which is not very well known. It's called signed least square estimator. So that's ordinary least square estimator. We just put signs inside, pluses or minuses, plus or minus 1 inside. So observations we like, we put +1. Observations we don't like, we put -1 for some reason. Because there are all these famous paradoxes with ordinary least square. That ordinary least square, all the Smith paradox and stuff like that. That with correlated observations, it's not very good. Sometimes it is good. So just to improve it a little bit, we use this estimator, which is almost ordinary least square. That estimator was considered by Noether, but it's not very well known. Nobody kind of uses it. So we used it very heavily actually in one parameter case. In one parameter case, it solves the problem, as I will show 1 or 2 slides later. So in addition to these standard ones, for some reason it's not enough for us to that estimators, and we use different type of estimator. We call it matrix weighted. We get, if this O is identity, then we have least square. Then we get ordinary least square. But we allow ourselves to play somehow with these weights in multivariate case. We don't need it in multi-parameter case. We don't need it in one parameter case. We can do this signed one. That's enough. And we want to keep these ones as easy as possible. So basically, we want to keep them identity. So for most observations, that will be identity or kind of identity, maybe minuses inside, like signed. So we want to be as close as possible to ordinary least square, and let's see how we will be doing with that, and where we need some corrections in multi-parameter case. So, and this is a very, very flexible estimator. You can put anything, basically anything, as long as M is invertible, you have unbiased estimator. Why? Because you put this X transpose XY, yes. X theta when you take expectation, and M and M minus 1 cancel. So you basically can put anything here, and you get unbiased estimate. And you get this variance. Okay. So not clear why we need that, but we will need that at the end. I'm not going to use that for some time, because I will do one parameter case, because to some extent multi-parameter case will be can be easily seen as generalization. Not very difficult, actually, generalization of one parameter case. So one parameter case is the basic and more philosophically more important. But I come back to that slide. Okay, one parameter model. One parameter model, we have only one parameter. We have only one function, no vectors. We can have design, but we use signed design. So we use ordinary design, but multiply, allowed to multiply our weights by -1 if we want to. And this is just Cauchy-Schwarz inequality. We can find optimal weights for this. So there is no convexity. I'll go to the next slide straight away. So this is a general criterion. This is still one parameter case. Xi is a design, signed design. But the problem already in one parameter case is not convex. That's why nobody was able to solve it in general. Only if f is constant, its location scale model, then this term disappears and the problem becomes convex, and it was solved for some whatever exponential kernel. That is a famous, actually, Grenander solution. It appeared in several places, and basically that was the only known case of optimal design. Okay, so if we have discrete space, then we can easily get these optimal weights, signed weights, because we are not sure if they are positive or non-negative. And Cauchy-Schwarz gives us that we don't need convexity. Cauchy-Schwarz is enough, and by direct checking, we can check that this is exactly the same covariance which blue has, because it's discrete and everything can be computed. So we have that the signed least square estimator gives the same result as blue, discrete blue. Okay, so how to compute? We have this sigma -1. That's the reason for the choice of kernels, this one. So whenever we can invert this matrix and then go to limits and blah, 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 then we can solve the problem. Otherwise, this is of course for general kernel, but next we need to do something with sigma minus 1. So we can do sigma minus 1 in that particular case. So Radoslav did it. But then after we struggled for quite a while, I found the solution in my book, which was 85, because I did it for something else. Of course, I've long forgotten it. And it was with Marina Kondratovich, whom some people know. She was my student. She's, what's her position? I don't know.
She's an MBA?
Yes, that one. Yes. So that was in her PhD. So it's a very useful result of inversion of some whatever strange matrices. Whatever the formulas, doesn't matter what formulas are. The fact that we can invert. And now the problem, next problem is go to the limit to get design, optimal design. Let's take these formulas and try to go to the limit. So we cannot actually take the uniform design. If we take uniform design, nothing works. We need to take quantiles of whatever Q function and stuff like that. But we can go to the limit and get the continuous optimal design. So approximate optimal design and continuous model. Now assume that we have AB interval. We have this signed measure because we solve the problem. We were solving problem for signed LSC. It's non-convex, as I already mentioned, but the careful consideration of these previous designs, when n tends to infinity and points are chosen in a strange way, show that we have some limits in distribution. We haven't even proved it that it's optimal design. We just know that it's a limit of some whatever procedure we constructed for finite number of points, but we can compute the limit. We cannot prove that the limit because we don't have optimality theorem, because it's non-convex criterion. We can have necessary condition, of course, and it's satisfied, but we cannot state it from these considerations.
Anatoly, if I can still ask.
Yes.
So when you say limit, so you have difference of dj, or I don't remember, if you go to the previous slide. So you have this difference q,
yes,
q, and so
yeah.
And so you have to make some assumptions that it's done in some kind of smart
way. Continuous, yes, continuous.
Across all intervals, because I can do limits at the ends of interval a little bit faster convergence. And in the middle.
No, you can't because I can only go to the limit when points are quantiles of this Q. So this actually denominators disappear because it's optimal configuration. That's optimal designs. Yes, sorry. The T. Okay. The points will be quantiles of this CDF with this Q function.
So the space of quantiles.
Yes. So anyway, denominators disappear.
Okay.
So denominators disappear. Otherwise, there is no chance to go to the limit.
Okay. Then.
So I'm just saying that somehow, if we go to the limit in some way, we will be able to get these formulas. I'm not claiming that they're optimal or anything. We just have some design. 2 slides later, I will try to convince you that they're optimal designs, but not yet. These are optimal designs. So what are the optimal designs? They have mass and the left point, mass at the right point, and some density inside, in the middle there. So,
what do you mean mass?
Mass means probability measure has, I don't know, probability 1/3 put points on A, probability 1/4 put points on B, and whatever density. Okay.
Correlations there 1.
This is some kind of whatever. So mass means positive probability of B naught at A.
Repeated observations.
I'm talking about continuous case. I'm not talking about realization. Realization is three slides later or 4 slides later. Okay. So, of course, that's the main discussion in a way. This will be the main discussion. So don't spoil my party. So that's not the main discussion.
But you need at least 2 for your party. Go ahead.
So here is point number 1. So I came to one positive aspect of all this. So far, there was only one, basically only one continuous design known. We had 2 or 3 more, but they were very particular cases in the other paper. In one parameter case. That was for location scale model, and for exponential correlation function, that was Grenander actually result, and Noether repeated, and Noether did several versions of the same result. Only one density. What was the density? It was uniform density in the interval AB, mass 1/3 with coefficient 1/3, 1/3 at the left point and 1/3 on the right point. That was famous example which was going from paper to paper, and that was the only one known. So that already gives you as many analytical optimal designs as you want for these kernels, for these UV kernels, but for any function, for any differentiable function, because you need because f comes here. So you need twice differentiable. But as Helge mentioned, because of his dual representation, you only need once. A differentiable function have to be differentiable once. So we can get already from increase the number of known particular approximate optimal designs for these models from 1 to as many as you wish. You just put any f and any u, any v, any interval, whatever, and you get. And we can generate just by Maple as many tables like that as you want. So mass at A, mass at B, and these are different cases for U and V. Parametric cases, whatever, anything you want. So that's the first advantage. Already in one parameter case, there were no 1 or 2 asymptotic optimal designs known for least square estimator or signed least square estimator. We have as many as you want. So there is no problem. You just put into this formula, some function. Maple will differentiate it for you, and you have the new optimal design. However, how to realize it? Because you remember, we cannot repeat observations. We cannot. It's kind of nonsense design because we cannot put many observations at A. So if you insist on using least square, then what you have to do instead of even in this location scale model, so that was optimal design. What you have to do, you have to put 1/3 observations here equally spaced, and 1/3 observations at point A, 1/3 observations at point B, but you cannot because you get you cannot get any more information. So you put lots of 1/3 observations very close to A, 1/3 observations very close to B. Yeah, eventually you will converge, but this convergence will be extremely slow. Eventually, yeah, we checked that. Eventually you will converge when n tends to infinity. Then you will converge to the blue, continuous blue variance, but it will be a long process. So the problem with least square is not that it's bad estimated. The problem is that this optimal density is very difficult to implement. So when you try to save observations, you say, why do I want 1/3 of observations here? Because it's 1 point. I put 1 observation here and uniformly spaced. It's bad design. It's bad variance. It never converges to what you want. You really need to put, if you insist on using on using the design, and that's the main difference, and that's why we needed these weights, different weights. We need to change. Basically, what we need to change, we will need to change weights at points A and B only. We don't need to change the weights in the interval, because we can take the quantiles of the CDF from this density, and then we replicate, we emulate the density, and it's fine. But we cannot emulate the masses. We need to give weights to these points, because if you look at blue from the LSE point of view, blue puts much bigger weight to the A and B, and that's the main difference. So if you insist on implementing that as we did in previous slides from the least square point of view, you have this difficulty of that discrete designs are very badly approximate this limiting measure. Otherwise, you still converge. Okay, I still didn't prove that designs are optimal. Okay, consider the case of Brownian motion. In Brownian motion, you see this Helga's formula, but you have extra f here, f of a divided by a, which Helga said 0. And for that, for Brownian motion, you can directly check the optimality of this design by using this necessarily sufficient condition of optimality, which you can find in some books on on Noether book, for example, on blue. So blue has to satisfy some condition. This is a blue measure, this one, I think. So you can directly check the optimality. And then, okay, optimal densities. Optimal densities are usually nice, this P, the internal bit, not the masses. Masses are always masses. But sometimes for some models like this one with the sign, because sign is intersect 0, so we can have this kind of densities, which means that we not only need density, but we need sign density, so that we need absolute value, and then we will need to assign signs to the points, not only to treat points as a quantile of the distribution. Otherwise, it would be almost a least square estimator. But for this kind of examples, which are not very typical, but for all these polynomials and all the other things, it's fine. It's positive density, or negative. We can always change sign. So my point is that for most cases, you can still treat our estimators as ordinary least squares, because we give weights 1 to inside, but we need to treat A and B in a special way. This is a picture, typical good picture. So because we have typical good pictures, typical bad pictures. So that one is a limiting continuous blue. That one is discrete blue, and that is Sachs-Silver-Sacre points.
Which one?
They swap in between. Sometimes we're better, sometimes Sachs is better. The crosses. Small means good, but here, for example, Sachs starts badly because it's asymptotic. In the first ones, you don't know, you never know. So sometimes it's worse than this crude point, these quantiles of our P.
And n is number of points?
N is a number of points, yes. For 2 points, n plus 2. So 2 means A and B, and n is a number. This is 2 points inside. So 4 altogether. This is 4 points, 5 points, 6 points, 7 points, because it's n plus 2. Because we treat A and B special way. So okay, one of the points is that, as Helge already mentioned, doing more than 10 points in most models is kind of waste of energy and waste of space and waste of resources, because for design for with correlated distributions, we never the variance doesn't go to zero, so variance goes to a constant, and we are quite close to a constant, to this constant. We have efficiency whatever we do. If we are not doing ordinary least square with no corrections, we get, okay, in this case 97%, whatever, or 96. That's what we were doing with Maria for the last 3 days for millions of models. Not these ones, but similar. The ones Helge was talking about, all these efficiencies of these designs. It's very quickly, we usually for 5 it's already, I don't know, 97%.
But this point set is Kiefer, Ylvi-Seeker and so.
What? No, because optimized discrete blue is better than Sachs. That will be in this one. Yeah, this one is optimized discrete blue. This is Sachs, and this is Sachs, and this is us. Here Sachs is better than us, but it's Sachs and Ylvi-Seeker points are always worse than optimized discrete blue. Well, optimized for points.
I can see that sometimes it's...
No, it's optical illusion.
Better glasses.
No, that's they all the
same.
Okay, you cannot see it's all the same.
Okay.
No, but actually, if you see carefully the middle of the cross, it's the middle, not the bottom of the cross.
Yeah.
It's the middle of the cross.
Okay.
No, that optimized discrete blue is always better. And to add to what Helge said, we basically always reach that as well if we implement with some corrections what Helge said in these blackboards. So we don't reach that because what we want to do here, we want to emulate least square, ordinary least square, not to go as far from ordinary least square. What Helge was doing, he didn't play that game in a way honestly. He used the answer and tried to go from the answer and said, okay, I try to use the answer, and of course he has advantage because he did not want to stay close to ordinary least square. We want to stay close to ordinary least square. We wanted just to correct it, and we can manage that in some examples quite nicely. In some examples, not. Okay, that's a general multi-parameter case and stuff like that. Yes, so that limit in design which I showed can also be obtained from the transformation, and that's a multivariate case already, multi-parameter case already as well, from the Brownian motion for these covariance kernels. So we can get basically optimal designs for all, whatever optimal design means, for all multi-parameter models using that basically what Helge showed on the blackboard, but with no assumptions at 0 or whatever f of a. And this is the covariance matrix, the covariance matrix of continuous blue. And we reach it by what? By playing with weights. These are our weights, which I said I will come back. If we come back shortly to this estimator, these are these weights, but asymptotic versions of these weights, O of x. And because I want to stay very close to ordinary least square, I only use weights, decent weights at A and B. But at all internal points, I only play with the design. And design is this P, the same P. Oh, sorry, wrong way. The design is this P function. This is my design. And this will be the weights at points A and B. So I still have optimal design problem. My estimator is not quite ordinary LC, but almost, because I only use signs. in multivariate case, I need to use not only +1, -1, but I also need to use zeros, because I don't like some points in some directions. So 0, 1, 0, -1, 1. Okay, so, sorry. So proof of that discussion or that all these models are equivalent in a way. So any model with triangular kernel can be reduced to Brownian motion, and then I will mention the Brownian bridge type models. Assume we have this model UNV, general UNV. It can also be written as VV and mean of QQ, because if t is smaller than t prime, then it will be q, and it will v divided by q multiplied by q will give us u, this u. Okay, so this is the transformation of variables. T equals q minus 1 of s. So if we write this model for this variable and divide by v of q minus 1, then we have this model. So 3 is exactly the same as 1, but in different time, and divided by this v function. The only thing we need to check is that that is a Brownian motion, and we check it just take an expectation. So if we take E of s and s prime, then we have v everywhere. The first v comes from this formula, and this v comes from our normalization, our denominator. So they go, and in the minimum, this is q of q minus 1. They go as well. So mean of s prime, it's Brownian motion. So the noise becomes Brownian motion, and that is our function, which in the previous slide I denoted f tilde. So in that sense, all these models are equivalent. We can go from any triangular to any other triangular. So we have all these cheap examples everywhere. How to incorporate conditionally Markovian process? We need to condition on some value of y at x0. So that will give us, for example, okay, consider that covariance function k of ts equals 1 minus absolute value t minus s on minus 1, 1. So if we condition that on value at 1, we get extra term. We should introduce new parameter in the model, which is a value of this of our noise, of our y into this point. Whatever point we take, it doesn't matter which point we take, 1 or minus 1 or whatever. So we need to augment our model by introducing one more regression function, and then our kernel will become triangular, and then everything will be rosy as usual. Now, so when I gave this talk in this room, it's recorded. You can see after this talk in the previous program, there was a very long discussion because the talk was about ordinary least square. My talk was about that paper with different kernels and stuff like that. And this time talk about this paper. And Helga talk is whatever, next paper. So, and the people who were very aggressive and very, I mean, unpleasant even after the talk were Henry, Luke, Werner, and they were attacking me with these papers, and they were saying this is all complete rubbish because everybody knows that ordinary least square is much worse than weighted least square, and it's all proven in these papers, and etc., etc., etc. So, okay, I agree with them, but not completely. Okay, least square, I agree only in one point. I agree that least square is slightly worse than weighted least square. With the rest, I don't agree. And I don't agree with these papers as well, because these papers are purely on the problem of constructing the worst optimal design, the worst designs for the least square. So they were not trying to consider typical or even uniform design or something. They were only considering the worst design for the least square, where least square has the biggest disadvantage against weighted least square, and this is not fair. Okay, in our examples, we have many examples. If we don't, and this is the only problem. Basically, okay, science is not a big problem, but this is the main problem. So if for fixed n, because we cannot deal with this problem, we cannot possibly match efficiency of ordinary least square to the weighted least square. However, if we introduce weights and signs, then we are almost as good as discrete blue. So yes, so to some extent, this is a kind of partial answer to that discussion. So what is how to slightly improve ordinary least square to get close to blue. If we don't improve, of course, we have many examples, and we did it with Maria as well. So this week we have many examples when indeed ordinary least square loses a lot to discrete blue. Otherwise it's almost as good. That's another similar plot to what I already showed. Another one of the same type. Here we lose slightly because in multi-parameter case, of course, many more cases we can lose more with this approach. We can lose much less with Hödger's approach because it's in a way.
What are the X's and the dots this time?
This is us. This is Sachs, and this is discrete blue, and this is
What is that?
Sachs is here.
Oh, is it better?
Of course, it's better. For typical problem, of course, it's better.
What do you call typical problem?
Typical problem is taken from because they never. Okay, come on. They are maybe not very good points, but they're using weighted least square. They use blue. We don't use blue. Remember, we use ordinary least square slightly corrected. Of course, we are worse. For typical problem, of course, we are worse. So what is the discussion?
Why just ask?
Okay. Of course, we are worse because we don't try to emulate. So if we try to emulate, the situation completely changes. No. When
Anatoly, I just want to be sure that it's not optical effect again.
No, of course. Okay, and yes, and that's a partial answer to the discussion: what is ordinary least square, what is weighted least square. And of course, if you follow, yes, I don't need that much. Sorry.
Okay.
If you follow the approach on the blackboard, which I don't know if I wanted to use some, I forgot now. Then you can get much better because you don't try to emulate ordinary least square. Okay, and English is very poor because and incorrect because I should have said thank myself for talking, not. But I have to say in proper English. Thank you for listening. Thank you.
Does anyone other than Val want to say something? If not, Val, do you want to say any more now?
No, I want to ask. So about Brownian bridge. So Brownian bridge, if I recall correctly, we have our Brownian motion.
Yes, with fixed. Yes.
Okay, so
Yes.
at this point there is no error.
Yes, but you don't know this value.
Why?
Okay, because you don't really know where you finish. Because Brownian bridge with unknown end. Okay. Okay, you want to finish, fine.
Brownian bridge I finished, so I place two observations. So I have function t square, whatever. And I put two observations, one on the left and another on the right. And I have
But you have perfect observations, you don't need anything.
Of course.
It depends on number of parameters, though. If you have 10
But
parameters.
still, obviously this design is the best one because my estimator has zero error.
Yes.
Good.
Yeah. Only if you have if you have not more than 2 parameters. Yes. But if you have 10 parameters.
Yeah, but in your case, you say it is not. Because you told that you can reduce all problem to.
Yes, but no. Whatever you do, you put 2 observations in A and B. There is no escape because they are always the best points and whatever. But then, if you want to use this technology, maybe if you use a different technology, if you want to use these triangular kernels, you need to introduce new parameter into model or whatever. Okay, maybe we talk about different Brownian motion.
Okay.
No, actually, I was talking about this model where the correlation is 1. Correlation is 1 after time interval 1. So which means you have exactly the same point. But when you fix the value of this point, then you become triangular. I mean, you become
Okay.
anyway.
Okay, well then I think that probably we all need our tea break after that. Thanks again to both of you speakers.
Thank you.